So last time we were working on the ratio test. That's pretty much the last section that discusses all the different techniques or tools to determine the convergence or divergence of a series. So we finished covering the 9th technique back in Friday. So today we are going to discuss the root test. Well, of course we cannot talk about infinite series and in particular the ratio test without talking about Ramanujan's series, Ramanujan's pi formula. Well, this ugly looking, this madness here, this series is an infinite series that if you compute infinitely many terms of this series and you multiply by the square root of 8 over 9801, the result is 1 over pi. This is so weird. Just look at that. So who could figure out a pattern like this? You know, like when we have like x to the first, x to the second, so sometimes it takes a while to identify the sequence of perfect cubes, the sequence of I don't know, powers of 3, etc. So, well, the history said that this mathematician Ramanujan, he used to dream about gods and goddesses that will tell him this kind of weird mathematical expression that he could apply to compute important results. And well, one of the most famous Ramanujan's series is the series right here, which converges to 1 over pi. So it's using computers to compute the digits of pi, right? Actually, well, up to this point, I think there's millions of digits of these decimals for pi computed, and I think it's based on programming this series. All right, well, so I think it would be a good exercise for you to take it home and use the ratio test to show that this series that converges. All right, of course, because there is a result for it. We're not going to do it here because that's going to take us maybe at least half a lecture to do. So in the meantime, we're going to look at the root test, and the root test is going to be exactly the same criteria as in the ratio test. So we're going to compute the limit. If that limit is less than 1, the series converges absolutely. If the limit is greater than 1 or infinity, the series diverges. Or if the limit equals to 1, well, the test is inconclusive and we need to look at another test. All right. However, this time we are not going to set up a very nasty ratio like we did in the ratio test. So in this case, actually the exercises for the root test are going to be a lot shorter than the ratio test. So we're going to take the nth root of something, of some sequence. You know, in this case, well, it's important to know that this is a good alternative for series that contain n powers. All right, and this is also an alternative to the alternating series test as we are going to look. That's why we're taking the absolute value of the general term, because that most likely will involve some alternating series. Well, so let's look at one example. Let's set up the limit. That is limit of the nth root of the absolute value of 2n plus 3 over 3n plus 2 to the nth power, close the absolute value bars, close the radical as n approaches infinity. Well, number one, notice in this case we don't have any negative terms for the series, nor we have any alternating factors, right? So in this case we can do two things in one shot. Number one, we can cancel out the nth root with the nth power. So that's why this root test is great for sequence, or rather for series that contain an n power, because that n root takes care of that n power. And then, well, we can also get rid of the absolute value bars because, well, we don't have any negatives or any alternatings. So this will be the limit n approaches infinity, 2n plus 3 over 3n plus 2. And well, this limit is 2/3 because it's polynomial over polynomial. the degrees are both the same, degree 1 in the numerator, degree 1 in the denominator. Alright, so well, again, for this root test, we have to look for three possible case scenarios. Number one, that limit we obtain is less than 1, greater than 1, or infinity, or equal to 1. In this case, it happens that 2/3 is less than 1. So for this reason, the root test tells us that it converges by the root test. Alright? So again, it just tells us that it converges. It doesn't tell us the value of the series in this case. Alright? So let's look at another example. Letter B. Sigma n equals 1 to infinity of n to the n power divided by 3 to the 1 plus 2n. Notice everything pretty much is in terms of n power, so that's why you want to use the root test to cancel out those powers n, right? Those n powers. So let's set it up. So that's a limit of the nth root of the absolute value of n to the n over 3 to the 1 plus 2n. Well, number one, in this case, we don't have any alternating factors, so we can get rid of those absolute value bars, all right? And then, secondly, well, I'm not going to cancel out this power n with the radical, with the index n, because, well, for the previous example, we only had one overall power of n, so we could do that as our very first step. However, here I would need to do some algebraic steps. And well, what are we going to do here? So number one, well, we can get rid of the absolute value bars, so that's good. That's all right. N approaches infinity. And that's the nth root of n to the n over, okay, this 3 to the 1 plus 2n is the same as saying 3 to the first power times 3 to the 2n. As n approaches infinity. And now, at this point, we may go about or in a way distributing the radical over the term in the numerator and the or the factor in the numerator and the two factors in the denominator. All right. So that's limit nth root of n over nth root of 3 and nth root of 3 to the 2n as n approaches infinity. Oh, that's n to the n power, by the way. Okay? And we may go about some cancellations, however, not yet. Let me have all terms ready to cancel this, alright? So, well, actually, let's do this one. Let's do this one. So, so for the last factor, the very last factor, whenever we have some x to the mn, this is the same as saying, or rather, I think it would be easier now. It would be easier if we write this x to the, okay, x to the nth root of x to the m. This is the same as the nth root of x, the whole thing to the m power. That is, we can write that m power that is on top of the variable inside of the radical as the whole thing overall. Alright? That means that we should and approaches infinity, so that's going to be n over, this is 3 to the 1 over n, and this will be 3 to the 1 over n, that's the radical, and to the 2n. And in this case, well, I think it's easier to see how we can cancel these n powers here. And this becomes a limit n approaches infinity, n over 3 to the 1 over n, and 3 squared, that's going to be a 9. So at this point, we we should evaluate the limit? Well, so number one, what's going to give us for the numerator? Well, infinity divided by some number, well, 3 to the 1 over infinity times 9, but 1 over infinity is 0, and 3 to the 0 power is 1. 1 times 9, that's a 9. Infinity over 9, well, we don't know how big this infinity is, and even if you divide it in 9 parts, I mean, it's still infinity. The root test tells us that the series diverges diverges by root test. Alright? So in this case, yes, we needed to play with the powers just a little bit before we were able to compute the limit. Alright. Let's look at the next example. Sigma n equals 1 to infinity. N over n plus 1, the whole thing to the n power. So let's set up the limit. Limit n, it's actually the nth root of n over n plus 1, the absolute value of that, to the n power as n approaches infinity. So, number one, there's a couple of things that we can do. Number one, get rid of these absolute value bars because we don't have any negative terms. We don't have any alternating series at all. So we can just get rid of absolute value bars. And also, in this case, we have one single power n that can be cancelled with their nth root. This will be limit n approaches infinity, n over n plus 1, and what's this limit equal to? 1. Well, what does the root test tell us about testing conclusive? Testing conclusive. Alright, so you would need to use a different test, any of the previous 9 tests that you learned in the previous sections. Alright. So when it comes to using the root test, more often than not you will run into some limits that, well, at this point in Calculus 2, you don't have to take them on a side strip to do the L'Hopital's rule and do like half a page for each individual limit. Instead, what we're going to do is use this special limit. So whenever you see something that looks like the nth root of n, that limit at infinity equals to 1. The nth root of ln of n, that equals to 1. The nth root of a, which this one we already used it in the second example or the third example. So you don't have to compute these limits using L'Hopital's rule because those are some of the weird ones that that will take a good minute to go. So just to verify the indeterminate forms that these limits give rise to, so that's well, that's the same as saying limit n to the 1 over n. Again, the denominator n is the index of the radical n in this case, n approaches infinity, and well, this is infinity to the 1 over infinity, but 1 over infinity, it's infinity to the 0 power, and that's one of the indeterminate forms that you learned back in Calculus 1. Another indeterminate form, well, very similar, limit ln of n to the 1 over n. That's ln of infinity to the 1 over n, or rather to the 1 over infinity. That's infinity to the 0 power, and again, that's one of the indeterminate forms you learned back in Calculus 1. But the very the third special limit, that's simply limit a to the 1 over n approaches infinity, that's a to the 1 over infinity, which is a to the 0 power, but any number to the 0 power is always 1. That's actually the special limit that we used in the third example when we raised the 3 to the 1 over n. So at this point, just use this limit. So don't actually, well, you might remember how it took like really long to compute this kind of limits when it came to these weird indeterminate forms. So just use this limit, all right? Well, so let's have a look at the very last example for this section. So that's limit k approaches infinity of the kth root. We're using k this time, not n, but it's going to work the same way. That's a negative 2 to the k times ln of k over k to the 10th power. All right. Well, in this case, the absolute value will be useful because notice we have some negative quantity to raise to the up to some power, and that will for sure output negative values. How is that going to work? Well, notice number 1. So let me write it on the side. Negative 2 to the k is the same as negative 1 times 2. I mean, negative 1 times 2 equals to negative 2. Raise that to the k power, and then this will be negative 1 to the k times 2 to the k. So we'll replace this in the next step of the limit. Limit k approaches infinity. That's the kth root of negative 1 to the k, 2 to the k, ln of k over k to the 10th power, but don't forget the absolute value bars. And in this case, these absolute value bars will be used to cancel out this alternating factor, because again, that alternating factor negative 1 to the k will negative 1 to the k will output negatives and positives 1. So those absolute value bars will turn all those negatives into positives. All right. So let's see, how do we simplify this limit? Well, limit, so that's going to be the kth root of 2 to the k ln of k, k to the 10th, as k approaches infinity. So we're going to distribute the radical over the two factors in the numerator and the one in the denominator. We're going to do that the following way. Space here. So that's limit. K approaches infinity, so that's going to be the kth root of 2 to the k times the kth root of ln of k over the kth root of k to the 10th power. So at this point, notice how we can cancel out the kth root with the k power for the first factor. This k ln of k will be one of those special limits that we have over here. However, well, it's in terms of n, but it's the same. You can have the letter k, the letter n, the letter m. It doesn't matter, your favorite letter. X even. So, but I'm worried about the denominator. So in this case, I'm going to use the same property of radicals to rewrite the denominator. This way, it will be a lot easier to see that special limit. Limit k approaches infinity, so that's going to leave us with a 2 times k to the, or k root of ln of k over kth root of k, the whole thing to the 10th power. So, and again, I think we can see the two special limits. Number 1, this special limit, I'm going to highlight it in pink, this one right here, and the other special limit, which I'm going to highlight in a different color so you can see how we're going to evaluate them. That is this first limit. And well, that's going to be this limit. So This limit will go to 1, this limit will go to 1, and that's going to leave us with 2 times 1 divided by 1 to the 10th power. Well, 2 times 1 is 2, 1 to the 10th power is 1, and the limit is 2. Because in this case this limit is actually greater than 1, the root test tells us that the series diverges. Alright? So this diverges by the root test. Alright guys, so let me just mention something important here. Actually, the root test, it was not a topic that we were supposed to cover. If you have access to the day-by-day schedule on Canvas, you will find out that for this section 11.6, we were supposed to cover only the ratio test. However, I covered the ratio test for 2 reasons. Number 1, we are ahead of schedule, so we have plenty of time to cover it. And number 2, I think it's an important topic for those of you who are maybe a math majors, and especially for those of you who are going to take higher levels of math, in which you will need an engineering course, a math for engineering courses. You may need to go back to infinite sequences and series, and having this, well, it's going to be a really powerful tool as another tool to solve some particular problem. This means that not 2 things. There's no homework on the root test, only the ratio test, and on the next exam, the 3rd exam, you won't be tested on the root test, right? Only the ratio test. But this was just an optional topic, but again, an optional topic that I decided to cover it. So that way also it gives you a sense of completion of all the 10 different tests, all right? In the meantime, let's go to another section. The next section, 11.8. 11.8. That's we're going to introduce a new kind of series, the power series. Well, what are power series? So number 1, so far we have worked with series. From sections 11.2 to 11.6. We work with series of constant terms. That is, we have this general rule in terms of n. We plug in some values of n to get the summation in terms of n. Those are constants only. However, these new power series are going to be series with a variable term. Well, what is that variable term? Well, surprise, is the letter x. That's the letter that we use very often to describe a variable. You know, that's something that depends on, well, more often than not, it's an independent variable, while the dependent variable is a variable y. Well, so this is how this power series look like. Well, essentially a sub n, that a sub n, which can be anything that looks like the series we looked in the previous section, like n squared divided by 3 to the n, but it's going to be it's going to go along with some power of x. And well, this power series will be turned into polynomials. These polynomials will be later used to compute approximations. And guys, you have done a little bit of these approximations back in Calculus 1, so you might remember linear approximations as one of the applications of derivatives. And you use these linear approximations to compute values like, I don't know, maybe the square root of 26. All right, and you got this square root of 26 in an exact form, but it was actually only an approximation. How do you do this square root of 26? Well, you had to compute the equation of the tangent line at some point, but not just any point, preferably at a point that is that is a perfect square that is close to 26. So you did the linear approximation at x equals 25. All right, and then you use that linear approximation to compute the square root of 26. You did something like the cube root of 65. Well, you needed to guess the function first, that's the cube root of x, and get the linear approximation or the equation of the tangent line at some value that is a perfect cube and close to 65, which in this case is 64. Then you use that linear equation to compute the cube root of 65, to approximate rather. However, back then they told you that this was only an approximation. And for example, can I use the same linear approximation to approximate the square root of 50? Well, the answer is no, because in this case, this number, square root of 50, is too far away from the approximation center at 25. In this case, there's two options. So, well, back in Calculus 1, they just told you one of the options. And the one option is to compute a new linear approximation. In this case, an approximation centered at a value closer, centered at a perfect square closer to 50. In this case, create a whole new tangent line at 49 and then use that linear approximation to approximate the square root of 50. But the other option is, well, that they didn't tell you back in Calculus 1, but I'm going to tell you this in Calculus 2, because that's one of the main objectives of this chapter, is to add more terms to the approximation. So in this chapter, in this class, we're going to use not only the linear approximation, we're going to extend this problem to the quadratic approximation, the cubic approximation, quartic, quintic, etc. So we're going to add more terms to the approximation, and well, that's an actual process that we call power series expansion. And we're going to use this power series to, well, as among other things, to compute these approximations. All right. Well, so these approximations can be centered at the origin. That's why you see this x squared, x cubed. That's basically x minus 0, x minus 0. Or you can center this power series at another value, which is the equivalent of centering these approximations at like 25 to compute the root of 26, for example. Well, what are these? What are these power series ultimately? So now this series will be seen as functions of x. And you know all the different properties of a function, you know, such as the domain, you know, how their behavior, you know, if they increase, decrease, etc. But we are going to be interested in the domain of this power series. All right, what is that domain? Well, we'll define it in the next couple of pages. In the meantime, let's work with this power series. How do we expand some of the terms? How do they look like? And then do the backwards process in the same way that we did it back in the section for sequences. Let's expand a few terms for each series, and in this case, starting at n equals to 0, this is x to the 0 plus x to the first plus x to the second, x to the third plus ... That's to indicate that this goes on forever, because we are not going to compute infinitely many terms, right? So, well, simplify if possible. Well, this x to the 0 is 1, x to the first, that's just x squared plus x cubed plus ... Right? And in this case, well, let's look at another example, one a little bit more elaborate. Well, -1 to the n. What's -1 to the n? Starting at 0. So -1 to the 0 power, that's +1 times x minus 5 to the n power, which in this case is 0, divided by 0 factorial. For the next term, n equals 1, that is -1 to the first power, that's going to output a -1, x minus 5 to the first power over 1 factorial, plus n equals to 2, -1 to the second, that's a 1, times x minus 5 to the second power over 2 factorial, and then, so notice the pattern. In this case, you don't have to calculate them anymore. So go plus minus 1 x minus 5 to the third power divided by 3 factorial, and then just go plus dot dot dot. That equals to, well, x minus 5 to the 0 power is it's a 1 times 1 equals to 1 divided by 0 factorial, which is 1. Well, that is going to give us a 1. All right. Minus, okay, x minus 5 to the first power, that's simply x minus 5. And 1 over 1 factorial, that's simply 1. And that's going to be x minus 5 quantity squared divided by 2 factorial, which is 2, and minus x minus 5 to the third power, which is divided by 3 factorial, which is 6. And of course, we don't have time to write down infinitely many terms. I mean, in this case, the pattern goes the same. We just denote it with these 3 dots. That's the purpose of those 3 dots. Let's do the backwards process. For the backwards process, well, we have a polynomial and we have to get the general rule using sigma notation. So, well, let's start with the sigma notation. Sigma n equals to 1 to infinity. We can start it at 1, we can start it at 0. That doesn't really matter that much. So, of course, this will involve some power x to the n, and in this case, I think the x to the n will work just very well, because notice how this first term has an x to the first power, and this is divided by an invisible one. Now, what we need to figure out is the sequence in the denominator. What do we have? 1, 8, 27, 64. Does anybody recognizes that sequence? Cubics, all right? N to the third power should work. Okay, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed, well, 125, etc. All right? Let's figure out letter B. Let's write it down in sigma notation. Number 1. What do I have here? Yes, I'm going to start it at 1 as well. To infinity, and of course, first of all, that involves an alternating factor. All right, negative 1 to the n power. Let's see if that works for the first term, for n equals to 1. For n equals to 1, that's negative 1 to the first power. Well, that's negative 1, so no need to add a plus 1 or a negative 1 to fix any issue. So this is good. Now let's find out about this 1, 2, 3, and 4, 5, 6. Number 1, there is an invisible 1 here that I would like to point out. And on the other hand, see how this coefficient 1 matches with the power 1. This coefficient 2 matches the power 2. This coefficient 3 matches the power 3. And of course, we can assume that this same pattern goes on the same way. All right? So that means that, well, there's a quotient here between the sequence of 1, 2, 3, 4, 5, etc. and 4, 5, 6, etc. So that means n in the numerator, x minus 5 to the n power, noted, because again, these coefficients match with the power. But what about the denominator? So for n equals 1, we get a 1 in the numerator. But how do we get a 4? What do we have to do with to the n so we can get a 4 in the denominator of the first term? N plus 3? And that does it actually. Yeah, plus 3. Right? That does it for this one. Oh, plus 5 as well. Thank you. Plus 5. All right. All right. So I mean, again, it's the same thing as we did back in section 11.1, but back then we did it with sequences. Here we're doing it again with, well, series. Well, it's technically a sequence with the addition symbol in between each term, and this time we're figuring out a pattern for the variable term. All Alright, that being said, what's the whole idea of power series? Alright, so number one, this power series, f of x equals n equals 0 to infinity of some a sub n times x minus a to the n power. We can think of this as a function, right? As a function f of x, and again, we need to recall all those properties of our function. Well, not all of them. One property in particular for function that we really care about is that of the domain. So, this f of x in general, f of x equals sigma n equals 0 to infinity, a sub n x minus a to the nth power, that's going to represent a function f of x into its power series representation. For example, we will find out that the function e to the x has some sigma representation. For those of you who may have seen this before, well, I think you know what they are. Also, the function sine x has a series representation. The function cosine x has a series representation. The function 1 over 1 minus x, which is one of the most important functions, has also a series representation. So it has a representation. And well, this interval of convergence is related to the domain of the function that it represents. Well, what's the connection? Well, so depending on the choice for x, well, we have two possible outcomes. One possible outcome is, well, plug in that value of x to a power series, and well, one of the possible outcomes is that we get a convergent series, or the other outcome is a divergent series. So in a very similar way that for regular functions of x, we found the domain of a function, and that domain of the function is the set of all values of x that will give us a defined value. And whether this is a fraction, a decimal, an irrational number, it doesn't matter. But we are looking at the intervals for which the function is defined. In a similar way, for the interval of convergence, we're going to look at an interval containing all the set of all values of x that will output a convergent series in this case. Well, let's do an example with the idea. For example, f of x equals 1 over x minus 4. Well, what's the domain of this function? Is this function defined for all values of x? No. Is there any restricted value? 4. So x cannot be 4. Alright? Alright. What if I want to evaluate this function at, say, at 5? Well, 5 minus 4 in the denominator is 1. That's 1 over 1. That equals to 1. So what does that mean? Is the function defined or not defined? It's defined, right? What about f? Evaluated at, I don't know, maybe 6. Six minus 4 is a 2 in the denominator. That's 1/2. Well, the function is defined, and its value is 1/2. However, what if we want to evaluate this function f of x at 4? That's a 4 minus 4 in the denominator. That's a 1 over 0. What's 1 over 0? Well, in this case, we're not computing a limit. We are evaluating a function. And so in this case, again, we need to recall the difference between the two. I know mechanically they look the same. Plug in the value, and if you obtain a value, well, that's what the limit is. But ultimately, limits exist or do not exist, and functions are defined or undefined. So in this case, undefined. Yes, it's undefined. Now, okay, this is what you guys learned back in intermediate algebra or college algebra, pre-calculus, well, you name it, all right? However, in algebra, you had guidelines to find these domains of functions. For example, the domain of a rational function, what did you do? Set the denominator equal to 0, solve the polynomial equation for x, and that value or values are going to be the restricted values, the values that you cannot input in the function because that's going to give you undefined. For radical functions of even index like the square root, the fourth root, the sixth root, the eighth root, etc., you set the quantity inside of the radical greater than or equal to 0, solve the inequality for x, and well, that interval is going to give you all the okay inputs for that radical function, right? And then for logarithmic functions, in a similar way than of the radical function of even index, you set the argument, that is the expression inside the absolute value, the logarithmic function. But in this case, you set it just greater than 0, not greater than or equal to 0, and solve the inequality. And that interval was the okay inputs. You know that's the domain of the function. So you didn't find the domain of a function by just plugging values to exhaust. Is that the way that you do until you get something that doesn't work? So that's why you learn all these guidelines, right? So now, what about power series? Let me make something up over here. F of x equals to sigma n equals 1 to infinity x over 3 to the n power. So, well, I think this series looks familiar. What does that look like? It looks like a geometric series, right? However, something's missing. The geometric series that you're used to are like sigma n equals 1 to infinity of 1/2 to the n, 7/3 to the n, 4/5 to the n. So what about that x? Well, this geometric series now contains an x, and it's now defining a function, depending on what we plug in for x, we may end up with something, not defined or undefined, but rather some infinite series that either converge or diverge. For example, let's try some values of x. For example, f of let's evaluate this at 1, f of 1. All right. So what about this geometric series? What would you say? Converges or diverges? Converges. All right, because the common ratio is a number below 1. In a similar way that f of 5 gave us a defined function. All right, did you see the connection? Did you see the analogy here? Well, let me check with another value. F of 2. F of 2 sigma n equals 1 to, or actually let me start it at 0 just to be consistent with the original geometric series, and that's 1 over 3. Well, not 1 over 3, that's actually a 2 over 3. Well, what about this series? Convergent or divergent? Convergent. It's another convergent series, right? Well, so converges in a similar way that f of 6 for this given function outputted an actual value. That means it was defined. Alright, let me try another value of x. How about f of not 3. Let me think of another number. F of 6 or f of 5. I think 5 is going to be more visual than the 6. Okay, what is this? Oh, that's not an m, it's an n. So, in this case, the series diverges because, well, what do we have? A common ratio that is larger than 1, and by the geometric series test, well, this will be a divergent But again, okay, here is the thing. Do we have the time to plug in every possible value of x until we find out whatever value or values that make a series diverge in a similar way that we have a function f of x for which we plugged in some values until we found out one that doesn't give us an undefined value? Do we have the time to do that? There has to be a process to find this interval of convergence in a similar way that we have different processes to find the domain of a function depending on whether this is a rational, logarithmic, radical of even index. So there has to be a way to get this interval of convergence, the set of these values that output a convergent series, and that, guys, is called the interval of convergence, and it's described here. And we have plenty of examples. However, we're going to look at this next time.